Hello everybody. In the last class, we discussed a little bit about countable sets and two or three results related to countable sets. We proved that if we have a countable or an enumerable set or an infinite set, whatever we call, each and every infinite set must have an enumerable subset. That was one result, an important result. And we finally proved the result that the union of a finite set and an enumerable set, the union of a finite set and an enumerable set is also an enumerable set. And by the help of that result, we can also prove that the union of a countable set and a finite set is also enumerable set or a countable set. Now, you see, this result can be extended further for finite number of enumerable or countable sets. So that is the result that we can say that if we have a finite number of enumerable sets, if we have a finite number of enumerable sets, I mean number of enumerable sets is finite. Over here we consider this kind of collection A1, A2, AN. Over here, how many such sets are there? N number of sets. So over here, this n, this number, is a finite positive integer. All right. So we consider a collection of what kind of collection? Finite collection. Finite collection of sets, like A1, A2, AN. And in this collection, each and every set is an enumerable set. That means A1 is an enumerable set, A2 is an enumerable set, similarly etc. AN, all these sets are enumerable sets. We shall have to show that the union of these sets, this finite number of sets, what kind of union? Of course, there is a union of finite number of sets. That's why we can say finite union. All right, we can write this as finite union. Finite union. All right, finite union of this kind of sets. What kind of sets? Of enumerable sets. Each and every sets are enumerable. So finite union of enumerable sets is also an enumerable set. We are going to show that finite union of enumerable set is also an enumerable set. How can we prove this one? We already proved the result that if we have two enumerable sets, if we proved a result that if we have a finite set and an enumerable set, then that union is also an enumerable set. Now, as a first step, we are going to prove the result that union of two enumerable sets. As a first step, we are going to prove the result that union of two enumerable sets is also an enumerable set, and afterwards we shall extend this result to finite number of enumerable sets. So we start with two enumerable sets. We start with two enumerable sets. We consider an enumerable set capital A and an enumerable set capital B. Both of them are enumerable sets. That means we can arrange them. We can arrange their elements in terms of a sequence A1, A2, AN. Similarly, we can arrange the elements B1, B2, Bn in this fashion. We can arrange the elements of these two sets A and B as a sequence. Now, first of all, we discuss the case when A and B are two distinct elements. they do not have any common elements. They are two distinct sets. That means A intersection B is an empty set. We consider this case when A intersection B is an empty set. That means they are disjoint. Alright. Now you see, whenever these two are disjoint, then their union A union B, this union can be arranged in this way. The elements of this A union B can be arranged in this way. First of all, let us write one element of first element of A, then the second element of B, then the first element, then the second element. Let us first write the first element of A and then first element of B, then second element of A and then second element of B, and so on. So we can say that the elements in odd number of position, the elements in odd number of positions, these elements are all the elements of the set capital A. Similarly, the elements in even number of position, these are the elements of the set capital B. Okay, so we can say that we can write this sequence as a single sequence C1, C2, Cn. How? We can say that in this sequence C1, C2, Cn, the odd number of elements C1 and then C3 and then C5, etc. This odd number of elements are the elements of the set capital A. So we can write C twice n minus 1 is equal to An, and the even number of elements, that means C twice n, this kind of elements C twice n is equal to the element Bn, for n is equal to 1, 2, 3, 4, etc. So following this rule, okay, following this category of rule, we can arrange the elements of the A union B in terms of a sequence. Whenever this A and B, whenever this A and B are two disjoint sets, two disjoint enumerable sets. This A and B, both of them are enumerable. So over here, what we have found, that the elements of A union B has been written in terms of a sequence, and therefore we can conclude that A union B is an enumerable set, as because it has the elements of this A union B has been written, elements of this A union B have been written as in the form of a sequence. We can say that this A union B is an enumerable set. So for this case, we have proved the result that A union B is an enumerable set. Alright. Now we consider this second case. In this second case, we take the sets A and B in such a manner that these two sets are not disjoint sets. Let me draw the Venn diagram. Suppose this is one set, and this is the second set. Okay, this is the common zone. Suppose this is the set capital A and this is the set capital B. Okay, now from these two sets, our target, we are trying to construct two disjoint sets. How can we construct two disjoint sets? Let us write this set capital A is equal to the set A1. Then this total shaded region, this is the set A1. Then the remaining part, what is this remaining part? The remaining part is B minus A. Alright, this is the remaining part, this much region. Alright, this much region is the remaining part. This remaining part B minus A has been defined as equal to B1. Okay, so from this Venn diagram, it is clear that A1 and B1, this is our this region is our B1. This is our set B1. Clearly B1 is a subset of the original set B. Hmm. Some elements in this common region has been deleted from the set B in order to make this set B1. Whatever it is, B1 is a set of the B1 is a subset of this enumerable set B. So because B1 is a subset of this enumerable set B, therefore either B1 is finite or it is an infinite set. Either B1 is a finite set or B1 is an infinite set. So if B1 is a finite set, then you see from this Venn diagram, it is clear that the union A union B can also be written as A1 union B1, where these two sets are disjoint sets. Now further, you see, if this set is finite, if this B1 is a finite set, then this total union is actually the union of an enumerable set and a finite set. We know that this kind of union, the union of an enumerable set and a finite set, this kind of union is always an enumerable set. We proved this result in the last lecture. Okay. Now, it may so happen that this B1 is not finite set. This is an infinite set. It may so happen that B1 becomes an infinite set. So it is actually infinite subset of an enumerable set. It is actually an infinite subset of an enumerable set, and we already proved in the last class that each and every infinite subset of an enumerable set is always an enumerable set. Again, I am saying that I proved in the last class that each and every infinite subset like B1 is a subset of the set B. Each and every infinite subset of an enumerable set like B is always an enumerable set. That means in this case B1 becomes an enumerable set, and A1 is equal to A, so A1 is also an enumerable set, and over here A1 and B1 are two disjoint enumerable sets. Therefore, by case 1 of this proof, in the case 1 of this proof, that whenever we have two disjoint enumerable sets, then their union is also an enumerable set. Therefore, by case 1, we can prove that A1 union B1, as because they are two disjoint enumerable sets, therefore their union is also an enumerable set. So if this is an enumerable set, then of course A union B is also an enumerable set. Alright, so in this fashion, by the help of previous results, we have proved that A union B is an enumerable set whenever, even when these two sets are not disjoint sets. So as a first step of the required target, what is our required target? Our required target is that the finite collection of enumerable sets is enumerable. So over here we have proved that only whenever we have two enumerable sets like A1 and suppose A2, in place of B I am writing A2, then this union A1 union A2, whether they are disjoint or not, it depends upon case 1 or case 2. Whatever be the case, A1 union A2 is an enumerable set. Now, if this is an enumerable set, along with this set, let me write it in a bracket. Along with this set, if we consider one more set, suppose A3, if we consider one more set, then that set is also enumerable set. If we consider one more enumerable set A3, we already proved that A1 union A2, this set is an enumerable set. Along with that, if we consider one more enumerable set, then the total union of A1, A2 and A3 is total union of A1, A2 and A3 is also an enumerable set. So in this way, we have proved that whenever we have three sets, A1, A2 and A3. Whenever we have three sets A1, A2 and A3, if all of them are enumerable, then their union is also enumerable. Again, along with this set, we consider one fourth enumerable set and take the union, and we can again conclude that the union of these four enumerable sets must be enumerable. So we continue this process, and ultimately, as because n is a finite number, we would be able to finish the process, and ultimately we would be able to conclude that this collection A1, A2, A3, etc., this collection of finite number of enumerable sets is again an enumerable set. So in this way, we can conclude that this union, we denote it by Cn, this union of finite number of enumerable sets is enumerable. Okay. So if in your exam you are given to prove this result that finite number of enumerable sets is enumerable, in that case, firstly you will have to write this theorem number 2.4, that union of two enumerable set is enumerable. Then you need to extend this result in case of finite number of enumerable set, as I have written in this corollary 2.3. So that was the first result I wanted to discuss today. I am coming to the next result. That means in this result, the next immediate question that comes in our mind, that we have proved that okay, union of a finite number of enumerable set is enumerable. If we have a finite collection of enumerable sets like A1, A2, An, then this finite collection of enumerable set is enumerable. Now the question is that if we have infinite number of such collection of enumerable sets, can we extend this result to infinite number of enumerable sets? Answer is we cannot extend this result, or at least this technique. We can extend this result, but the technique of the proof would be a bit different from this result, because if we try to continue the proof following this technique, then this technique would never be finished, because over here n was a finite number. That's why we successfully finished the process. But if we want to prove this result for infinite number of enumerable sets, over here we considered finite number of enumerable sets. But if we want to extend this result for infinite number of enumerable sets, then we cannot follow this process. We need to adopt some different mechanism. So how can we prove these results? Let me show you the result as a corollary. So you can also consider this one as an independent theorem. Although I have written this one as a corollary, but you can also consider this one as an independent theorem. Over here, it has been proved that the union of enumerable number of enumerable sets. Okay, how many such sets are there? Innumerable number of sets are there. Over here, you see in this collection, how many such elements are there? And these are innumerable number of elements. The dot 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 has been written, so it is not finishing over here. It is going on and on and on. So this collection is not a finite collection. This is actually how many such sets are there. These sets have been written in terms of a sequence. So this collection is actually an enumerable collection of sets. Now, what kind of sets? Each and every set would be enumerable set. Each and every set would be enumerable set. So we can say that we have innumerable number of enumerable sets. We have innumerable number of enumerable sets. So enumerable means we can arrange them in terms of a sequence. We can arrange them in terms of a sequence like this. So each and every element in this sequence, they are actually enumerable sets. So as because this A1, A2, An, all of them are enumerable sets, therefore the elements of A1, A2, A3, etc. they can also be further arranged in terms of a sequence. Suppose the elements of A1, they have been written as a sequence with two indices. The first index is fixed over here, a small a11. These are the elements of the set A1. A11, then A12, A13. Over here, the first index. This first index does not change. All right, the first index denotes this index of the set, and the second index changes. All right, so this kind of sequence where we have two different indices. Why did we consider two different indices? Because if we consider the second elements of the second set, in that case these elements can be written as A21, then A22, A33, just like we arrange the elements of a matrix with two indices. Over here, just for our convenience, we have taken the first sequence as the first index as the index of this set A2, so that whenever we look at the elements at a glance, we can consider them as the elements of matrix, like A11, A12, A13, etc. How many such elements are there? Infinite number of elements are there in each and every row. So these are the elements of A1, these are the elements of A2, and similarly these are the elements of AN, and so on and so forth. All right. Now this kind of elements, whenever this kind of elements having two indices, whenever we want to, if it is possible to arrange them in terms of a sequence, if it is possible, I am not claiming that this is possible at all. If it is possible to arrange them in terms of sequence, then what would be the form of sequence? Aij. Aij, certain arrangement technique or certain rule must be followed. Over here, I and j both should vary from 1 to infinity. Okay, so this kind of sequence, when following certain rule, of course, in between I and j, I am going to tell you the rule after later on in the second part of this proof. But if it is possible to arrange this kind of elements having two indices in terms of a sequence, then such sequence are called double sequence. All right, such sequences are called double sequence. So over here, if it is possible to arrange the elements, all these elements, if it is possible to arrange all these elements, all these elements would together construct the union of these sets. What is our target? Our target is to show that the union of these sets is an enumerable set. So if it is possible to arrange all these elements in terms of a sequence, maybe double sequence, whatever it is, it doesn't matter. It is actually a kind of sequence. So if it is possible to arrange all these elements in terms of sequence, then we can easily conclude that this union of these sets A1, A2, A, etc., union of all these sets is an enumerable set. Okay, so that is the blueprint of the proof, that our target is to arrange these elements in terms of a double sequence. And in order to prove this result, we are dividing this proof. We are actually this over here, you see this A1, A2, AN. These sets may be disjoint, may not be disjoint. All right. So we are trying to introduce a mechanism by which the union of these elements, union of these sets, can be represented as the union of disjoint sets. Okay, one mechanism has been proposed over here. I am going to show this mechanism by the help of finite number of sets. Over here, n number of elements have been n number of elements are there, but let me show you the process. How can we arrange them? Let me first of all show you the process with only 4 elements. Afterwards, I would show you the technique or the rule in between I and J so that they can be arranged in terms of a sequence. Now you see over here, let me show you over here in this software, in this MS Paint. Suppose we have, for the sake of discussion, we have only 4 sets. And let me draw the picture of these sets. Say this is one set. Now we consider, say this is the second set. Say now, say this is the third set. Now suppose this is the fourth set. Now you see, I am trying to shade this region by a certain color. What kind of shade? You see, let me shade them in this fashion. Suppose I am shading this one by this kind of color. What is this? What is this? You see, this is the set A1. Suppose let us call them these sets A1. No, not yeah, A1, right? This is the set A1. Suppose then the second set is, suppose A2, not B, A2. Then suppose the third set is equal to A3 and the fourth set is equal to A4. Now you see over here the blue, not blue, the yellow shade. What is this yellow shade? This is the original set A1. Okay, so let us define this new set B1, B2, B3, B4. Yet I am trying to define 4 sets so that the union does not change. But they, these newly constructed sets, these sets are distinct or disjoint sets. Okay, so let us define B1 is equal to this set A1. Now let us choose another color. Now you see, I am trying to shade the region, this much region. What is this much region over here? Over here you see, this much region is actually set, let us call it the set B2. What is B2? B2 is equal to, you see, that can be written as A2 minus A1. If you look at this picture, this is the common region in between A1 and A2. I am just considering the region shaded in this over here as a green color. So we can call this region is actually the region from the set A2, but we are not considering the common region in between A1 and A2, this much common region. So we can say that this is actually our region A2 minus A1. If you if in this technique, if you have any question, immediately you can stop me and you can ask me your question. I am continuing the process. Now let us shade this one by another color. Suppose I am considering A3. These are this much. The part of A3. The part of A3. We are considering the part of A3. How? You see this shaded region by this kind of color. This shaded region we are defining as B3. B3 is equal to, what is this? I am choosing certain part of A3, and how much we are deleting. We are not considering the previously shaded region. The previously shaded region is actually the part of A1 union A2. All right, this much was the previously shaded region. So we can say that we are actually deleting A1 union A2, or the part of A1 union A2 hmm, from this A3. Okay, so in this way we can construct B3. And similarly, if we consider one more set B4, how do you define? B4 is equal to A4 minus the union of A1, A2, A3. And you see these these three colors designate the union of A1, A2, A3. So we can say the remaining portion, say this is the remaining part, the portion whenever it is deleted, A1 union A2 union A3. Okay, this much remaining part. What is this? Let me initiate this region by this kind of color, say this color. So you see, we have four different sets. This first set represented by blue in this yellow color. This first set is actually the set A1. This yellow color, this is the set A1. Then this green color, that is the set not A1. Rather, I should write them as B1. So B1 is equal to A1 over here. Okay. Now this region is our B2. Then this region is our B3, and this region is our B4. So what we have, you see the total union, the A1 union A2 union A3 union A4. This total union is now represented as B1 union B2 union B3 union B4. But over here in this second representation, each and every elements or each and every components or each and every sets involved in this second union B1, B2, B3, B4, all these sets are disjoint sets. All these sets are disjoint sets. So we can write them in this fashion. Union. This union can be written as AI. Union of AI, I is equal to 1 to starting up to 4, from starting from 1 to 4. That can be written as the union of this BI. I is equal to 1 to 4. All right. So if you continue this process, if you continue the technique following this mechanism, you would also be able to construct finite number of sets, whatever it is, up to n number of sets, so that this B1, B2, Bn, this newly constructed B1, B2, Bn would be disjoint sets, and the union of these sets AI starting from I is equal to 1 to n, whatever be the value of n. Maybe over here I have taken n is equal to 4, you can take n is equal to 5, then 6, and so on for any positive integer. You can write this union is equal to this bi, union of bi, I is equal to 1 to n. I is equal to 1 to n. So over here this bi should be disjoint sets. So we can start with sets like A1, A2, A3, A4, where these sets are not disjoint sets. This A1, A2, A3, A4 may not be disjoint set, but from that disjoint set we can extract or we can construct such disjoint sets, so that the total union does not change, but these sets become disjoint set of each other. These sets become disjoint of each other. So we can start with disjoint sets. We can start with the sets which are not disjoint at all. Whatever be the process, we can follow this mechanism and construct such disjoint sets, so that the total union does not change. All right, that's why in this proof we can without any loss of generality we can consider that these sets are also disjoint, because even if these are not disjoint, In that case, we just need to undergo through this kind of process, so that ultimately we will be able to construct such disjoint sets. So it is immaterial whether you take disjoint sets or the sets which are not disjoints, or you can say overlapping sets. If you take overlapping sets, from that overlapping sets you can easily construct disjoint sets like b1, b2, b3, b4. Clear? That's why over here we can say that these sets may be disjoint, may not be disjoint, it doesn't matter. Hmm. So without any loss of generality, we can say that these sets are disjoint sets, because if they are not disjoint, we can consider this kind of operation, and ultimately we would be able to construct disjoint sets, so that the total union does not change. Our main target is to keep the total union. The total union does not change. Clear? But we can say that originally we are starting with disjoint sets, because if they are not disjoint, we can follow this process and make out of that disjoint out of that sets we can make or extract certain disjoint sets, so that the total union does not change. Why we are stressing on the fact that the sets would be disjoint? Because if we have disjoint sets, then the manipulation becomes much more easy. So without changing the union, we are just saying that the sets are can be taken as disjoint sets. All right. So that is the first part of the proof, that over here these sets a1, a2, an, if they are disjoint, it is fine. If they are not disjoint, in that case also we can extract these we can extract or construct certain sets, so that the total union does not change, but the sets b1, b2, bn becomes disjoint sets. So it is better, for the sake of simplicity, it is better to assume that originally we are starting with some disjoint sets. Clear? That's why I have written over here, you see, without loss of generality. Without loss of generality means whatever case we consider, it doesn't matter. The total set, the total union does not change at all. So without loss of generality, we assume that these sets AI are all disjoint sets. Okay, so that is the first part of the proof. So now let's continue the remaining part of this proof. The remaining part is not much difficult. You see over here, uh, if we suppose that this a1, a2, an are disjoint sets, then all these elements are not repeated. What I am trying to say is that this a13 will never arise in the remaining portion. So now I am trying to arrange these elements a, I, j in this fashion. You see, I am trying to draw a line. You see, at first I shall write a11, then comma, then I may write a12 or a21. I don't know. I need to make certain rule, so that whether a12 or a21 will come. What I am trying to say is that I would firstly consider these two indices. Over here we have two indices. Over here I is equal to 1 and j is equal to 1. So at first I would follow this kind of rule, that maybe this is one element, let us call it a, I, j, and maybe this is another element, let us call it a, what the notation I have followed, akl. All right, let us call it a, k, l. Now our target is to arrange all these A11, A12, A13, etc. in terms of a sequence, but that should follow certain rule. Okay, I am trying to develop that rule. Now in this kind of arrangement, if Aij comes first and after that AKL appears, then what would be the rule? We are trying to make this kind of rule. You can also make different kind of rule, it doesn't matter. I'm just proposing one rule, that I plus j should be less than k plus l. That should be the first rule, that I plus j should be less than k plus l. Say, let us call it rule number 1. And if by chance I plus j becomes is equal to k plus l, then what happens? Then we should consider I less than k, this kind of rule. If by chance, if I plus j becomes is equal to k plus l, then we should first consider the what is the first index. What is this rule? Now if you follow this rule over here, you see, if you follow this rule, you can check that a11 should first come first. A11. Why? Because all the remaining indices, if you sum up the index of A1, 2, we have two indices. 1 plus 2 is equal to 3. Then 1, 3. 1 plus 3 is equal to 4. Over here, A21, A22. So over here, A11, 1 plus 1. 1 plus 1, I is equal to 1, j is equal to 1. 1 plus 1, that is 2, is always less than the sum of any other indices. You can consider A12 or A21. So if you compare them, we have 1 plus 2. So this is the rule we have. A1 plus 1, that is less than A1 plus 2 or A2 plus 1. But if we have a tally in between these two elements, say over here, you see, we have a tally. We have a tally in between A1, 2, because the total summation of these two indices is equal to 3. 1 plus 2 is equal to 3. And A2, 1, the sum of these two indices is also is equal to 3. So now it comes, you can consider this as the element Aij, and this is the element AKL. Okay, so we now need to consider this second rule, because over here this 1 plus 2 is equal to 3, this 2 plus 1 is also is equal to 3. So I plus j becomes is equal to k plus l. And therefore we can say that over here, which element should we first consider? Over here we have two elements, A12, and the second element is A21. Now which element should come first and which element should come second? Over here, this is the value of I, this is the value of j. So I is equal to 1, j is equal to 2. And this is k, this is l. Let me write them over here. Over here, I is equal to 1, j is equal to 2, then k is equal to 2, and l is equal to 1. Now you consider this case. Say this is our Aij, this is our Aij, and this is our AKL. Here, this is our Aij, this is our Aij, and this is our AKL. Now you see over here, I plus j and k plus l both are same. So we have to consider this second rule. What is the second rule? The second rule says that I should be less than k. What is I? Over here, I is equal to 1 and k is equal to 2. Therefore, this is the first element that should come immediately after A11. So over here A12 should come, and afterwards A21 should come. Here, so over here, whenever we have tally in between, whenever we have a chance of confusion in between two indices, in between two elements, then this is the second rule that will resolve the confusion. And similar confusion would appear if we consider afterwards what we have. If you consider, let me write it over here. If you consider three elements, you see this is the rule. This is the rule that I have written. This is the rule number 1 and this is the rule number 2. Firstly, we need to follow the rule number 1, and if the rule number 1 fails, then we need to follow the rule number 2. Now you see over here, if you consider the elements A, 1, 3, then A, 2, 2, and then A, 3, 1. These are the three elements where 1 plus 3 is equal to 4. Again 2 plus 2 is equal to 4, and again 3 plus 1 is equal to 4. So over here, out of these three elements, which element should come first? You see over here, if we consider this element as equal to Aij, and this element is equal to Akl, then what is I? I is equal to 1, J is equal to 3, K is equal to 2, and L is equal to 2. Okay, so over here we can say that I plus J becomes is equal to K plus L. Now if it happens, then I should be less than K. We need to concentrate on the first index, this index and these two indices, I and K. So over here 1 is less than 2. Okay, so A13 should come first. Similarly, this element 2 is less than 3. Therefore, A22 should come second. And finally, this A33, that should come third. So in this way, we need to resolve the position whenever we have this kind of situation when I plus J becomes is equal to A plus L. So you see over here in these three elements, this sum of the indices is always equal to 4. In these two elements, the sum of the indices was equal to 3. And over here we have a single element where the sum of indices is equal to 2. Now we have 4 elements, this kind of elements, where the sum of these indices become is equal to, sum of their indices become is equal to 5. You see 1 plus 4 is equal to 5, then 2 plus 3 is equal to 5, then 3 plus 2 is equal to 5, then 4 plus 1 is equal to 5. So how to resolve them? In that case, we need to look at the first index. This is the first index 1, so it should come first. Then the second index is 2, then it should come second. Then the third index is 3, and the fourth index is 4. Here, so in this way, we need to resolve their position. So this is a group where the total summation is equal to 5. So we can continue the process, and if we continue the process, what we observe that the elements of the total union can be represented as a double sequence. And the elements of this double sequence, what are these elements? These elements of this double sequence, these are the elements in the form I and J. And what is the rule by which we arrange their elements? This is the rule by which we arrange their elements. Over here I have taken less than symbol. You could also take this greater than symbol, it doesn't matter. So I am not saying that this is the only rule by which a double sequence can be arranged. There may be other kind of rules by which a double sequence can be arranged. I am just proposing one rule here. So by this rule, what we observe that the union of this total union, that means the union I is equal to 1 to infinity ai. This total union has the elements of this total union have been arranged in terms of a sequence, and therefore this total union is an enumerable set. Clear? So in this way we can prove that the total union is an enumerable set. And as a corollary, in case of enumerable set, if this result is true for the total union, this kind of result can also be true only for finite union. Okay, because this is actually an infinite union. If it is true for infinite union, then it must be true for a subset of such a finite number of elements. And even if you, in place of this ai over here, this ai were enumerable sets. If you consider some finite sets or particularly or specifically countable number of sets, if you consider only countable number of sets, if this ai are finite or enumerable, that means if this ai are countable, even then that result holds, that we can say that this kind of enumerable countable union of countable sets countable. So we can have this corollary, the last this corollary, countable number of countable sets is again a countable set. So that is the technique I wanted to discuss over here. And as a last result, let me just introduce this result, because the rule over here is more or less same. We can prove that the Cartesian product of Cartesian product of two countable sets is countable. What is this? Say we consider one set P, another set is Q, and then what is Cartesian product? P cross Q. P cross Q will have this kind of element in the ordered pair, like Pi and Qj. Pi and Qj, where Pi, the first element, is actually the element of this first set, and Qj is the second element of this second set. Okay. Now you see, what is this? PIQJ. We have again two indices, I and J. Therefore, the technique I demonstrated in the previous theorem, considering the same rule. Over here, you see, I have proposed the same rule. We can just whatever. What is the difference? In the previous proof, we had only the elements like Aij, and in place of Aij, we have Pi, Qj, this kind of element. And in place of KL, we have PK and QL, this kind of ordered pair. So it doesn't matter whatever with the representation, Aij or PIQJ, it doesn't matter. Just we need to arrange them, and this following the same rule, we can arrange them. We can arrange them. We can arrange these elements like PIQJ. This is the arrangement. You see over here, this summation is equal to sum of indices equal to 2. Over here, this sum of indices is equal to 3. Over here, this sum of indices is equal to 4, and so on. So what we observe? We observe that this union, this is actually the cross product P cross Q. This cross product, the elements of this cross product can be arranged in terms of a sequence, and that's why the element of this cross product, is also a countable set or enumerable set. So in this way, in the same technique, we can prove that the Cartesian product of two countable sets or an enumerable sets are also enumerable. So this much I wanted to discuss today. So that's all for this lecture. Thank you for being with us.